Today's video is often one of the more challenging topics of the year. We'll look at work. Those of you that have seen it in physics might have a little bit of an understanding of it, so it might be a little bit easier for you. So in everyday language, work means the amount of effort you're required to perform a task. In physics, the technical meaning depends on the idea of force. What you can think of it as is the force of describing a push or a pull of an object. So maybe you're pushing a book across a table or the downward pull of Earth's gravity on a ball. In general, an object moves along a straight path with a position function s of t. We've seen that a lot. The force is defined by the acceleration. Your force is equal to the mass times the acceleration. So this is a formula that you're going to want to know. Now, the units will play a huge role in helping you in work problems. First, let's talk about if our units are metric. Well, your mass unit in metric is in kilograms, your displacement or distance is in meters, and your time is in seconds. The unit of force is what's called a newton, and is abbreviated with N. So your force unit for metric is newtons. If you're using the English system, the US system, our force unit is in pounds. So notice, if they give you pounds, that's already a force. You don't have to do mass times acceleration. It's directly giving you a force. If you have constant acceleration, then the work is just the force times the distance. Now, our units, if we're using metric, our work unit, well, we did a force was in newtons, a distance which is in meters, so you could call it a newton meter, or usually what that's referred to is a joule. So joule, or a newton meter, is our unit of work for metric. If we're in the US system, we're multiplying by our pounds by feet, so we'll see it as foot-pounds. So this is a very important chart. It'll help you in lots of problems. Our units of force. Well, let's first look at the metric. Our unit of force is a newton. And our unit of work is the joule, which is sometimes called a newton meter. Now, if we're in the US system, our unit of force is a pound. LB, if you don't know, is our abbreviation for pound. And our unit of work is the foot-pound. The problems can be made much easier by looking at the units and seeing what they are giving you. So let's say we want to know how much work is done by lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high. And we'll use, because we've got kilograms and meters, we know we're working with metric. So therefore, we know our acceleration due to gravity is 9.8. So work is equal to force times distance. We first need to find the force. Well, the force is equal to mass times acceleration. Our mass unit is kilograms, which we have 1.2 of, times our acceleration due to gravity, which is 9.8, which will give us 11.76. This is a force, so therefore it is a newton. To find our work, we'll take that force, the 11.76, and multiply it by the distance it's traveling. Well, it's traveling 0.7 meters, so we'll do times 0.7, and that'll give us 8.232, and you can label that either a Newton meter or a joule. So J would be the abbreviation for joule. Now, what if we wanted to lift a 20-pound weight 6 feet off the ground? Notice we're using a US system. We have pounds and feet. And it's important to note that a pound is already your force. So we've already got a force, so work is just force times distance now. So our work is just 20 times 6. So we get 120, and our units is foot pounds. It's important to note in the second part, we did not have to multiply by gravity because we're given the weight, which already includes gravity in it. It's a force. And it's not a mass. So a key thing is to know that when you're given pounds, that's already directly the force. You don't have to do a mass times an acceleration. So the force being constant times the distance gives us the work. Well, what if the force is not necessarily always constant? Well, let's suppose we have some object moving along an axis, the x-axis, in the positive direction. And that force is not constant. So we'll call our force function f of x. Well, what we can do is we can divide that function into a bunch of small intervals of equal width, delta x. We can pick sample points from them. And then f of those sample points will give us our forces in each section. Hopefully you kind of see where this is going. Okay, when we've split things up, picked sample points, when we had equal width, this should eventually become an integral, hopefully you recognize. We've seen this several times. So your work is going to be your force function times that width delta x. Well, that'll just become our dx in our integral. So the force function is just what we will end up using. So as our number of sections approaches affinity, just like we've seen in all the other ones, that will eventually give us our integral. So, because we've been doing integration this whole second half of the year, and you probably recognize that when we split it up into a bunch of sections of equal width, take sample points, we've seen that ends up giving us our integral. And I should just mention here again, the f of x is representing the force function here. So let's try this example. We've got our force function as x squared plus 2x pounds. So we know we are working with US here. Well, you just have to do the pounds, which is your force, times your distance. Well, the distance for us is the dx, essentially. So in our integral, we're going to be going from 1 to 3. Our force function is x squared plus 2x. And then the distance you can think of as the dx. So we just have to evaluate this integral, and this will tell us how much work is being done. So we'll have 1/3 x cubed plus, this will become an x squared times a half out front. 2 times a half is just 1. We'll evaluate from 1 to 3. So we'll have 1/3 times 1 cubed plus 1 squared. Oops, sorry, 3, not 1. 1/3 times 3 cubed plus 3 squared minus 1/3 times 1 plus 1 squared. Make sure that second part is in parentheses so that we distribute the negative. 3 cubed is 27. Divided by 3 is 9. 3 squared is 9. We'll have minus a 1/3 plus 1. So this will be 18 minus 4/3, or 1 1/3, you can think of it as. So that will give us 16 2/3. We had US, so our work units is foot-pounds. So now we're going to look at Hooke's law. Hooke's law deals with springs, and what Hooke's law says is your force, F of x, is equal to some constant k times x, where x is the distance beyond the natural length that the spring is stretched. So every spring has some natural length. If you stretch it, it's going some distance beyond that natural length. So here, if we say our natural length's at 0 and it's stretched this section, this distance here would be our x, because that's how far it goes beyond the natural length. So it's key to note that x is the distance beyond the natural length. And this law holds true as long as x is not too large. So a force of 40 newtons, so we've got newtons, so we know we're dealing with metric, is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 centimeters to 18 centimeters? Well, the first thing, when we're working with newtons, our distance unit needs to be meters. So we need to convert each of these centimeters into meters. Well, there's 100 centimeters in 1 meter, so all of our decimal points will just move over 2 spots. So this will be 0.1 meters. This will be 0.15 meters, making this 0.15 meters, and this will be 0.18 meters. So we need to make sure our units match up, because in work we'll have Newton meters, not Newton centimeters. Now, in spring problems, the first thing you'll always do is find K. Well, we know F of x is equal to Kx. Well, F is our force, which they told us was 40. We're looking to find K, and x is the distance it's stretched beyond its natural length. Well, the natural length here was 0.1 meters. We were stretched to 0.15 meters. So that means we went 0.05 beyond the natural length. When you divide the 0.05 over, we will get that K is equal to 800. What that means is our force function is now just 800x. And remember, the force function, we're putting that into our integral to find the work. So we'll now do our integral. The key thing is, for our values, we need to be the distance beyond the natural length, because that's what x represents. So in the problem, if we want to go from 0.15 meters to 0.18 meters, 0.15 meters is 0.05 beyond the natural length. And 0.18 meters is 0.08 beyond the natural length. So your values always have to be the distance beyond the natural length. We had our force function was 800x, and then we've got our dx. So we've just got to take the antiderivative now. This will become an x squared, multiply by a half out front. You get 400x squared, evaluated for 0.05 to 0.08. So we will have 400 times 0.08 squared minus 400 times 0.05 squared. And when we punch that in, we will get 1.56. We were working with metric, and this is a work, so we will have either joules or you could say Newton meters. So again, what this gave us was the work that would be done to stretch the spring from 0.05 beyond its natural length to 0.08 beyond its natural length. Our next example, we're going to take a 200-pound cable that's 100 feet long. It hangs vertically from the top of the building, and we want to know how much work is required to lift the cable to the top of the building. Well, the work to lift the parts that are close to the top is going to be different than the work to lift the parts further from the top. So therefore, it's not constant. So what we'll do is think of splitting this rope into a bunch of tiny parts, each delta x in weight, in length. Well, because we had 200 pounds and 100 feet, so we had 200 pounds and it was 100 feet long, that means we have 2 pounds per foot. So our rope here is 200 pounds per feet. And in a lot of these problems, you're going to have to set up some type of axes. So we're going to say 0 is at the top, and x is the distance from the top. Well, pounds is our force unit, so we need to somehow get a pounds. Well, if you have 2 pounds per feet, you need to multiply by some number of feet to get it to be a force of just pounds. Our distance, or that it needs to travel, is x. So therefore, to get rid of the 2 pounds per feet, or the feet of that, we'll have to multiply by x feet, and that'll give us that our force function is 2x pounds. So now when we put this in our integral, our force function was 2x. We'll have the dx. The dx is really coming from the delta x, the width of that little section. You can think of it as, technically what we did is we split the rope up into a bunch of tiny little sections. We took some point in that section and found the work to get that point up. Well, when those sections become smaller and smaller, when they go towards infinity, that just becomes an integral, just like everything else we've seen. To find our values for the integral, we've got to decide where could our possible distances from the top have been. Well, if you're at the very bottom of that cable, you would be 100 from the top. And if you're at the very top of the cable, you'd be 0 from the top. So our values would be 0 to 100. And now our integral is set up. And when we evaluate this integral, this will give us the work that it will take to get the entire cable to the top. And again, the reason we had to do the integral is because each section of the cable requires a different amount of work to get it to the top. So this is a pretty straightforward integral. We'll have an x squared, so we have to multiply out front by a half, times 2, which will give you 1. And we have to evaluate from 0 to 100. So we'll have 100 squared minus 0 squared, which will give us 10,000. Because we had US, we are going to be foot-pounds. So our last example, we are going to have a tank that's in the shape of an inverted cone. The height of that cone is 10, the radius is 4. And the cone is filled with water to a height of 8 feet. So in other words, or 8 meters, sorry. So in other words, there's a gap of 2 meters in between the top of the water and that base of the cone that's at the top. What we're going to do is we're going to find the work required to pump the tank out the top, the entire amount of water out the top. Essentially, we're going to do like we did with the cable. Each slice of water, each horizontal slice of water there, is going to take a different amount of work to get to the top. So we've got to think of it as we split them into a bunch of different slices. Those slices get thinner and thinner as we have more and more of them, and we should recognize that's going to eventually become an integral. So we'll do an integral just like we have for the other things. One thing they give us is that the density of the water is 1,000 kilograms per meter cubed. So note we are working with metric here because we have kilograms and meters, and that's what we're going to start with, this density of the water, and we'll be able to piece it together from there what our integral will be. So we started with 1,000 kilograms per meter cubed. Well, kilograms is our mass unit. To get rid of the meters cubed on the bottom, we need to multiply this by some volume. When we do that, the meters cubed will cancel out, and we'll have just a kilograms amount, which will be our mass, which we can then work to get towards our force and then our work. So we need some volume. The volume that we are going to use is the volume of our slice of water. As you can see in the picture, that's basically a disk. Our volume of that slice is going to be the area of the circle that's the face times the thickness delta x. Since it's a circle, we'll be doing pi times some radius squared times the thickness delta x to give us our volume. The radius that we want is this distance right here, which we can call r. Well, some things that we have in this picture. We know that our whole height of the cone is 10. Our entire radius is 4. We have that the radius we want we'll call r. And this length here, if the distance each slice takes to get to the top is x, that means this blue distance must be 10 minus x, because you're chopping off the x that it needs to get there from 10. What we have here is two similar triangles. We have the big triangle, which has a base of 4 and a height of 10, and we have our smaller triangle with a base of r and a height of 10 minus x. So what we can do is we can set up a proportion. We can do 4 over 10 equals, the 4 relates to r, as 10 relates to 10 minus x. Well, we want to get r by itself, because we need to know what our radius is. So we'll multiply both sides by 10 minus x. The 4/10 I'll rewrite as 2/5. 10 minus x equals r. And again, all I did was reduce 4/10 to 2/5, multiplied both sides by 10 minus x. Well, this allows us to find, or to plug into our volume. We said our volume would had to be pi times our radius squared times delta x. Well, we know what our radius is equal to now. So that's going to be pi times 2/5 times 10 minus x, all squared, times our delta x. Well, if we square both those parts, we'll really get 4 pi over 25, because 2 squared is 4, 5 squared is 25. We'll have 10 minus x squared, and we'll have our delta x. So what this is our volume. Well, we said we had to multiply our density of the water times our volume, because that would cancel out our meters cubed and just give us a kilograms. So we're going to multiply this by our 1,000 kilograms per meters cubed, our volume. When you do that, we will get 160 pi 10 minus x squared delta x. And keep in mind, the units for this now is kilograms, because the meters cubed cancel out. Well, a kilograms is the mass. To find the mass, we need to do, or to find the force, we need the mass times the acceleration. So we need to multiply this times our acceleration of gravity, because we're trying to pump the water up. So we'll multiply this times 9.8. Well, the 9.8 can multiply with the 160 out front. That'll give us 1568 pi. We'll still have the 10 minus x squared delta x. And because we did a mass times an acceleration, this is now a force in metric, so this is a number of newtons. Well, to find the work, we just need to multiply it by the distance it's going to travel. Our distance each slice has to travel is this x amount. So our work function then is just multiplying this by x. So we'll have 1568 pi. I'm going to stick the x in here. Again, that's the distance it has to travel to the top. We'll have 10 minus x squared and delta x. So this is our function we'll use to find the work. We'll put this in an integral. When we put it in an integral, the delta x will become the dx. And because the 1568 pi is a constant, I'm going to pull that out front. So we'll have x, 10 minus x squared. The delta x becomes dx. And now for the values that we have. The values for your integral should be the minimum and maximum distance that your slices would have to travel to get out the top. Well, if you're at the very top surface in our cone's water, you would only have to travel 2 meters to get to the top. But if you're at the very bottom point in our cone, you'd have to travel 10 meters to get to the top. So therefore, our integral values are going to be 2 and 10. And now we just have to evaluate our integral. Well, first we'll FOIL out. So we'll have 1568 pi, integral from 2 to 10. We'll have x times, when we FOIL it out, we'll get 100 minus 20x plus x squared dx. We'll distribute that x through. We'll have 100x minus 20x squared plus x cubed dx. And we'll evaluate this integral now by taking the antiderivative, keeping our 1568 pi out front. We'll have x squared, so we have to multiply by a half out front. A half times 100 will give us 50. We'll have x cubed, so we'll multiply by a third out front, giving us negative 20 over 3. And we'll have 1/4 x to the fourth. This will need to be evaluated from 2 to 10. So we'll have 1568 pi. We'll plug in our 10. Remember to put your whole second part in parentheses when you plug in the 2. Now, when you plug the first part there in, all the parts with the 10, you should get 833 1/3. Minus the parts with the 2 will give you 150 2/3. When you subtract the inside there, you'll get 2048 over 3. Multiply by the 1568 pi, and we get 3211264 pi over 3. Now this was metric. We just found a work, so that means this is joules. Now if you punch that in your calculator, what it would be 3,362,827.797. And that would be joules again. Joules are Newton meters, you could say. So the key thing with these is recognize your units, decide what you need to do with your units to get to something we can work with. We needed to get to a mass. To get a mass, we needed to multiply by a volume, so we found the volume of our slice. Then we multiplied by our acceleration, because mass times acceleration gives us a force. Then we took our force and multiplied it by the distance the slices needed to travel, which was x, and we used that to find our integral. That's it for today's video. We'll see you next class period.